So today I want to talk to you about laws of exponents. If I start going through them one by one, the first one I want to talk about is the product rule. It's pretty basic. You have the same base, and they have exponents. You add the exponents. So the explanation is just keep the bases the same. The base stays the same. And you're going to add the exponents. So you have x squared y z3, might be hard to see. If you have an x y squared z, if I have the same base, so this x and that x, I'm going to add the exponents. So here, this one doesn't have an exponent showing, but the default is that there is one of those x's, so there's a 1 exponent. So x squared and an x, if I add the 2 and the 1, I would get a cube. So I have x to the 3rd power. I do the same thing for the y's. I have a y to the 1st power, because there's always the default of 1, and a y squared. So 1 plus 2 again is 3. Here I have a z to the 3rd power, and a z to the 1st power, so I end up with a z to the 4th power. So that would be my end answer for that problem. For this one, 4 is a normal number, so I would multiply it by whatever number is in here. And the number in front, there's just one of these items, so it would be like 1. So 4 times 1 would be a 4. If there was another number sitting in front of here, like a 2 or a 3, I would multiply them, just like normal. These two terms are being multiplied, so I would multiply the numbers in front like normal. X squared and an x to the 1st power gives me an x cubed. And then I have no y's over here, but I do have a y squared, so I still have to show that I have a y squared there. That would be the first one. Sometimes they like to show expanded forms. So when it talks about an expanded form, what it's saying is, if I take this x squared, I could really write that x squared like x times x. Then I have a y. Then I have a z cubed, so z times z times z. Then I have another x, and they're all being multiplied, so I keep the multiplication symbol. I have 2 more y's. And then I have a z to the 1st power. So I'm just showing you this one so that when I use the same rule over and over again, you can kind of see where it's coming from. So the idea of having an exponent is that you're telling whoever's looking that I'm going to take whatever this base is, and I'm going to multiply it by itself the exponent number of times. So when I saw x squared, I knew I should multiply x times x. See, I had 2 x's there because I had a squared. So in the end, I really want to go and count all of my x's. So I have an x, an x, and an x. I have 3 of those x's total, so that's why I would write x cubed. And if you notice, that's what I ended up with here is an x cubed. So I've kind of used those terms, they've gone away, so I don't really have to use them again. Now I want to think about my y values. So I have a y there, and a y there. So I had 3 y's, so once I use them, they're also gone. Then I have z's, and if I think about how many z's I have left over, if I count them, I have 1, 2, 3, 4 z's. So that's why I had z to the 4th power, and that matches exactly what we had. So this was called expanded form. And sometimes things might call for you to write it in expanded form. Expanded form just says that however many of the bases you need, the exponent will tell you that. You just write them all out. You just list them all out. So sometimes that helps to explain why things are the way they are. So if we move to the next one is the quotient rule. And the quotient rule is very, very similar to the product rule, except instead of multiplying like bases, you are dividing like bases. So you're going to do very, very similar things, but instead of adding, you're going to subtract. And the way I keep these, and I tell them apart, is since multiplication and division are opposites, adding and subtraction are opposites. So it sort of helps me to remember that when I multiply, I add, and when I divide, I subtract, because it can get very confusing. So for this one, I have one example, and I want to go ahead and show this expanded. So I have x cubed. That tells me I have x times x, all divided by x squared, which is x times x. And the idea is, if you are multiplying and dividing by the exact same thing, you're not really changing the number. That's like saying if I took the number 2 and I multiplied it by 3. 2 times 3 is 6. Well, if I then take that number and divide it by 3 again, 6 divided by 3 would give me 2. Well, you go back to where you started. Multiplication and division are opposites. So if I multiply via the top and divide via the bottom, I'm really not going anywhere. They cancel each other out. I take one step forward just to take one step backwards. So you don't really go anywhere. So since those two are opposites, they cancel each other out. And if you notice, the same thing happens here. And I have one left over on top. So that would give me just x, or x to the first power, because there's just one of them there. So if I think about writing that the other way, using the rule where I use subtraction, I would have x to the power of 3 minus 2. Because in my head, you can either do it in your head or you can write it down, I would be subtracting the exponents. So 3 minus 2 would give me the 1 that's the exact same thing as up here. I still just have 1x. So I can write the 1 or I cannot write the 1. Either way, it's the same answer. So that's the second rule. The third rule gets used a lot. This is power of a power. And what this rule says, if you have some base and it already has an exponent, and you raise that whole thing to a separate power, you end up multiplying the exponents. You multiply the powers. So you keep the bases and multiply the exponents. So to show you just one example, if I have r cubed, I would get r to the 3 times 2, and 3 times 2 is 6, so you end up with r to the 6. Now if I showed you this in expanded form, the reason that this works is if I have r cubed and I want that quantity squared, that tells me that I want everything inside of here to be written twice. So that means I have r cubed times r cubed. Well, if I write it like this, then I'm using rule 1, and I'm saying, okay, well, I add the exponents, so I get a 6. I can also do the expanded thing that I did before, and I could say, well, that's r times r times r. That's this first one. Times, and I can do the second one, another r times r times r. And then, of course, I collapse it back together again, and to do that, I would just add up all of the variables I have, all of like variables. So 1, 2, 3, 4, 5, 6. I have r to the 6, and that's exactly what I have there. So in some of my videos, I say that in mathematics we like to be lazy, in that we don't like to do more work than we have to. So if you notice, expanding is a lot of work. Sometimes even writing this down is a lot of work. So we use rules to help us simplify some of the things that we know are going to happen because of the way rules work. So the power to a power rule is just a simpler way of doing the expansion. I don't want to have to expand it every single time, so instead I'm just going to know that if I have a power raised to a power, I multiply the exponents. So if I look at this example down here, I have m5 raised to the third power. So instead of having to separate that into m5, 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 I'm just going to use the rule. So the rule says I'm going to take the same base and I'm going to multiply the exponents. So 5 times 3 is 15, so I would end up with m15. And that's that rule. The next one is power of a product. So what that means is you have certain things on the inside and they're all multiplying each other, and they're all being raised to an exponent. Then I just distribute that exponent to each of those things inside. So the parentheses are what you want to be aware of, because you want this exponent to get distributed to everything inside of the parentheses. So you distribute the exponent, and it says use rule 3 if needed. And rule 3 says if there's already an exponent there, you have to multiply the exponents. So we look at a real world example right here. I should say a real example. I want this exponent to get distributed to all of the exponents inside. Now, I'm showing you this particular example to try and hit a few things that students tend to do wrong. So this negative goes with the 5. It doesn't have to, but that negative is inside the parentheses, so it needs to get squared. One of the easiest ways for me to do that is to think about this as a negative 5 squared, because the negative 5, the 5 already has a power of 1. 5 is a base. Any base, if it doesn't show a power, has a power of 1. Just like this s here has a power of 1. So this really, when I distribute this, this is like negative 5 squared. And then I have r squared squared. And then I have s to the first power squared, and t cubed squared. So you see how I took this square on the outside, the 2, and I distributed to every single thing on the inside. And sometimes it helps to put the 1s in there so you know not to forget to distribute to those items. It's very easy to forget that. Now you individually take and evaluate if possible. So over here I have a negative 5 squared. And since the negative is inside the parentheses, that means I include it when I go to square it. So this tells me I want a negative 5 times a negative 5. And a negative times a negative, since they're the same sign, would give me a positive. So I actually end up with a positive 25. And then r squared, this is where I have to use this rule 3. I have to multiply these two exponents, right? I have to multiply the exponents. So 2 times 2 is 4. So I have r4. And then this s had an imaginary 1, so 1 times 2 was just 2. And sometimes if you don't write the 1 there, you might forget to distribute the 2. You just write the s. So you got to be careful. This t cubed, again, I'm going to use rule 3 up here and say I'm going to multiply those exponents. So 3 times 2 is 6. So all of this is equal to 25 r4 s2 t6. Okay, this rule is very similar to the last rule. We distribute the exponent and maybe use rule 3 if necessary. This just says if my parentheses here, if my parentheses include the top and bottom of a fraction, they're not just over the top and they're not just over the bottom, but if they go around all of the fraction, this exponent gets applied to both the top and the bottom, the numerator and the denominator. So if I imply that, if you notice, these already have exponents, so I'm going to need to use rule 3 and multiply. So I have to not only multiply the 2 to the 3, and 2 times 3 is 6, so I have x to the 6 on top. But I also have to take this 2 and bring it to the bottom and multiply. So 2 times 4 is 8, so I end up with y to the 8. So you got to be careful on that rule. Multiply if needed, distribute to top and bottom. Okay, so the 0 exponent rule. This one I wanted to pause this paper to explain why this rule works. This is one that So many people get confused, and it's hard to remember the rule, but I think it helps if you understand why the rule works to try to remember what the rule is. So pretty much the rule says whatever's on the inside of these parentheses, if the exponent on the outside is 0, so any base to the power of 0 is 1, which your brain likes to think, oh, if it's a 0, maybe it's 0, but it's not, it's 1, and I'll show you why. So if we just get this 0 exponent rule, there's a few ways we can deal with this, and all of them are good, valid ways. So I can deal with this by just expanding it out. I mean, they're numbers, so maybe I can actually do it. So here I have 2 times 2 times 2 over 2 times 2 times 2. And I can start canceling if I want to. 2 divided by 2 is 1, 2 divided by 2 is 1, 2 divided by 2 is 1, and I get 1. An easier way to think about it is if I actually do 2 times 2 times 2. So 2 times 2 is 4, and then 4 times 2 gives me 8 on top. 2 times 2 is 4. 4 times 2 is another 8 on bottom. And any number divided by itself is 1. If I have 8 pieces and I need to divide it among 8 people, each person gets 1 piece, right? 8 divided by 8 is 1. So there I've just shown using a number and expanding it out that if it's the same exponent, I get a 1. And if I think about the rule that we just learned, specifically the quotient rule says, well, if I'm dividing, which I am, I would subtract my exponents. Okay, well, let's do that. So I have the same base. It said to keep the same base. And I'm subtracting the exponent. So I have 3 minus 3. And 3 minus 3 is 0. So that's why that 0 rule comes in, if I have an exponent of 0. Well, I just learned that anything to the 0 power is 1. And since my problem didn't change, my result shouldn't change either. The idea behind the 0 power is exactly what this division rule is saying. Is if I have any number divided by itself, right, like 8 divided by 8, the answer should be 1. So the 0 exponent rule says I have that base and it was dividing by itself. It had the exact same exponent. That's why it was a 0. So if we apply that to my x's, so I have x to the 4 y cubed over x4 y. If I think about what's going to happen, if I expand these out, I have 4x's on top and 4x's on bottom. I can also just say that I have x to the 4 minus 4 and y to the 3 minus 1, because there's always going to be a 1 there. And 4 minus 4 is 0. 3 minus 1 is 2. And anything to the 0 power is going to give me 1. And we're lazy in math, so we don't always like to write a 1 if we don't need to, so the answer would just be y squared. And if I come back up here, you see how I have the same thing on top and the same thing on bottom? Well, if I multiply and divide by the same thing, those just go away. They cancel each other out. And that's what the 0 is implying. The 0 is implying that somewhere along the lines, this was happening. So if I come back, this 0 exponent rule that we just discussed, if I have a negative 3 to the 0 power, all of this negative in the 3 is inside the parentheses, so all of that becomes 1. Over here, and I put this one on here for a reason, if you notice there's no parentheses. Only the 3 is to the 0 power. The negative is not included, is not inside parentheses like it was up here. So this negative stays separate. I still have that negative. That doesn't change. But the 3 to the 0 power does become a 1. I put this example on the bottom, 2,768 x to the 4th y z cubed. All of that inside parentheses to the 0 power, because all of that becomes 1. It doesn't matter what the base is. If that base is being raised to the 0 power, it's 1. It could be a million. And if it's raised to the 0 power, it's 1. Okay, so the last rule that I'm going to talk about in this video is the negative exponent rule. The negative exponent rule just says if you have a negative exponent, you're going to write the reciprocal. And if you write the reciprocal, it becomes positive. So over here, if I have just a normal base and the exponent is negative, I flip it over the fraction bar, and now it's 1 over x to the a. So instead of a negative a, I flip it over the fraction bar, and it becomes a positive xa. And the other happens. If it's on the bottom of a fraction, and it's negative, you flip it to the top, and it becomes positive. And if you notice, there's no fraction bars here. But that's because you can always write any number over 1. So if I think about keeping that fraction bar in the exact same spot, there's a 1 in front of here, so the 1 will stay, and all of this is going to get moved to the bottom, and instead of a negative exponent, it becomes a positive. The same thing happens down here as I move it to the top, and then I don't have to write the divide by 1. So if I look at my examples, I have 4 to the negative 3. Well, remember I could write that as 4 over 1, because when I divide by 1, it doesn't change, so it's equivalent. I'm going to write the same fraction bar, but my 4 has to be on the bottom of the fraction bar, because the negative is in the exponent. So I have a 4 cubed, and I have to put the 1 on top as a placeholder. The next example, I want to have to make sure you understand when things move, because I see a lot of students who mix things up. So specifically, when you see a negative power, that should tell you that whatever your base is, it's in the wrong spot. That if I have a fraction bar, top or bottom, if it's a negative, it's in the wrong spot. So if it's a negative on the bottom, that means it's in the wrong spot on the bottom, and you need to put it in the right spot. So move it to the top. Once it's in the right spot, it's no longer a negative exponent because it's in the right spot. So the negative exponent only tells you that it's in the wrong spot. So if I look over here, I'm going to have that same fraction bar. The fraction bar is not going to move. Does the b have a negative exponent? Well, right now there's no exponent, and the default exponent is 1. Is the 1 negative? No. So the b is going to stay put. The b does not move. And then I ask, well, I have this z. The z has a negative exponent, so since it has a negative exponent, it's going to move to the bottom. So I'm going to move it to the bottom. And once it's on the bottom, it's a positive exponent. So it's just a regular 2. And math grammar wise says that my alphabetical letters should go left to right. So if you want to start writing them, B would be first, X could come next, then Y, then you would move your Z. That way you know it looks right in your answer. So X has a negative exponent, so the negative exponent tells me it's in the wrong spot, so I want to move it from the bottom to the top. So X to 5. And if you notice, now that it's in the right spot, it's no longer a negative exponent. I look at the Y, and does the Y have a negative exponent? It has a positive 1, so the Y would stay put. As one more example, if I had 3x negative 2. I've seen students get this one wrong, so I want to make sure to mention it. Again, the 3 itself, just like when we were talking about this 5 up here, the 3 has an exponent. A lot of students like to move all of this to the bottom. Well, the problem with moving all of that to the bottom is the 3 has a positive 1 exponent. If it moved to the bottom, it would then have a negative 1 exponent because it's in the wrong spot. So be very careful with your constants. Make sure that if you're going to move something, even a constant, that you're moving a negative exponent. So this has a positive 1. So because it's a normal number, the default is that it's sitting on the top, and I don't need to change it, so it's going to stay on the top. This x is a negative exponent, so that will move to the bottom. So that's the answer I get for that one. So this is the basic laws of exponents. I'll have another video. You can click the screen. I'll link them when I get it. And I'll go ahead and have some examples where they're using multiple rules, maybe 3 or 4 rules in one. That way you can see kind of how all of these rules come together to get applied. Make sure to subscribe. Have a great day. Bye.